So this is the review for exam 3. Before I get started on the review, I want to mention, number one, the exam is very similar to the spring 2019 exam. And number two, there's a little typo here on the very last slide of the review slides that I sent you. So in review 3, the very last slide, slide 16 of 16, here where I said we're given the position function, I actually meant the velocity function. So, and in this problem here, this function that's given shouldn't be s of t over here, but v of t. So this, in the original set of slides I sent out, this was s of t, but it should be v of t. And since we're on this slide, we might as well just review it. So in this problem, we're being asked for the total distance, okay? So if you look at the integral of the velocity times time, this would give us what's called displacement, if you just integrate the velocity. Because here the velocity is allowed to be positive or negative, because it's just a velocity function. And so you might have a particle that's moving forward, and then it moves backward, and then it moves forward. And if we just integrate the velocity, it doesn't take into account the overlap, and the definite integral of the velocity gives us what we call the displacement. So for total distance, we have to integrate the absolute value of the velocity. So now this function is always greater than or equal to 0. So it's always moving to the right. We don't get any, moving forward and then moving backwards. There's no overlapping of its trajectory. And so this will calculate the total distance. And of course, the only reason I put this example in the review sheet is because of my, strange obsession with the absolute value function, which I take any excuse to review the definition of the absolute value. So here, to do this integral, the number one thing I would warn you against doing is just ignoring the absolute value bars. A lot of students will just ignore the absolute value bars. They'll just copy the absolute value bars and then integrate the inside like nothing, like everything's okay. So don't do that. Don't ignore the absolute value bars. Unwrap the notation, right? We ask ourselves, what does the absolute value of root t minus 1 actually mean? So you remember, absolute value of blah is equal to blah if blah is greater than or equal to 0, and it's equal to negative blah if blah is less than 0. And so all I've done here is spit out the definition of absolute value where blah is root t minus 1. And then here, I move the 1 over and move this one over here also. And if you look at the graph of square root of t minus 1, so this is root t minus 1. Oh my God, I'm trying to write, it's terrible. And if we take the absolute value, so this is root t minus 1. And so this is 1, right? So I just took the square root function and flipped it, shifted it down 1. The absolute value, we're going to take this part down here and flip it up. So anything that's negative, so if I take this part gets flipped up, and then that would be the graph. So I want to, so from 0 to 1, you see it's the negative of root t minus 1. And for t bigger than 1, it's just the regular function root t minus 1. So that's how I'm able to get to this definition. I think maybe using the graph is the easiest way. And so now if you look at the definition here, the function changes, what it looks like around the number 1. So if I'm to the left of 1 or to the right of 1, that'll change what the function looks like. And I'm integrating from 0 to 4. So I have to break this integral up. Between 0 and 4, we're crossing 1. So, and the function changes its definition at 1. So I do an integral from 0 to 1. And we use the appropriate definition when t is less than 1. You have 1 minus root t. So here's the integral 0 to 1. And then 1 to 4. And I've plugged in the appropriate definition, in each region. And this is how we integrate an absolute value function. You figure out where it's positive and negative, and then you break it up into those regions, and where it's negative, you're going to put a minus sign in front of the function because you want to make it positive. And then the rest of it is just doing antiderivatives using power rule, and then f of b minus f of a. And I hope I didn't make any arithmetic mistakes. Usually the students have no problem up to here. And then this part can be the tricky part, doing the little arithmetic, it's always easy to make a little error. So yes, my apologies. I didn't mean the position function. I meant the velocity function. And I have to think about what the integral of the position function is. So anyway, being able to integrate an absolute value function in general, that's an important skill and an important problem, and something you should definitely know. And the trick is to break it up. So, let me go back to the beginning of the review. Here I have a local extrema problem. Just from a theory point of view, local extrema is very important. If you can read between the lines there. So yeah, how do we find the local extrema, as opposed to absolute extrema? Basically, when we're asked to find local extrema, all they're saying is find the critical points and then classify them. And we classify them either with first derivative test or second derivative test. Okay. So here, I'm going to take a derivative. And the first comment I want to make is, rather than take the derivative of this function in its original form where I'd have to use a product rule, I decided to distribute the x to the 2/3 and take the derivative of that. Why? I thought about it. I thought about, if I do a product rule here, just in my head, I thought about it a little bit. You'd get these messy terms, you'd get two terms, and I'd still have to simplify it. And so I just distributed first and then took the derivative. Here, I'm just using the power rule. The derivative of x to the n is nx to the n minus 1. And so I get my derivative here, 4/3 x to the minus 1/3 minus 5/3 x to the 2/3. Here, if we're just looking for a derivative, we could stop here. But I know I'm going to need to figure out where the derivative is 0 and undefined, because I'm trying to find critical points. And I noticed this has a negative exponent, which means it's a fraction. And so basic, rule of algebra is to combine the fractions. And so this second term, I need to have the correct denominator. So I multiply this second term, top and bottom, by x to the 1/3. Because I already have the 3, I need the x to the 1/3. So I multiply top and bottom by x to the 1/3. In the numerator, when you multiply x to the 2/3 by x to the 1/3, we add the exponents. That's x to the 3/3, or just x. So here I get 4 minus 5x over 3x to the 1/3. This is my simplified derivative. And the whole reason I like to simplify it into one fraction here is I know now that this fraction will be equal to 0 when the numerator is equal to 0. And I know the numerator will equal 0 when x equals 4/5. And I know this fraction will be undefined when the denominator is 0. And we can see that the denominator will be 0 when x is 0. And here, if you look at the original function, the domain is all reals. That's x squared, and then we're taking a cube root. So here, there's no issue. The domain is all reals. So the numbers 0 and 4/5 turn out to be critical points here. 4/5 makes the derivative 0, and 0 makes the derivative undefined. And so as a general comment, when we find critical points, we then want to classify them. Usually we don't find critical points just for the sake of it. Sometimes there are some artificial problems in the calculus textbook, they say find the critical points. But in practice, we find critical points and then we classify them. We want to know what's happening at the critical point. Okay. So here you have an option. We can classify with either first derivative test or second derivative test. In this case, I look at the function and I go, well, I don't want to take the derivative of, this messy function here, 4 minus 5x over 3x to the 1/3. So here I'm going to just do a first derivative test. So I'm plugging in numbers in between the critical points. For example, here to the left of 0, I picked -1 and plugged it in. You see the denominator will be negative. the numerator will be positive. You get 4 minus 5 times -1, or 4 plus 5. So the function is negative to the left of 0. In between 0 and 4/5, for example, I picked 1/5. You know, anything over 5, so that when you plug it in, the 5 up here, this 5 will cancel. So here, if I plug in 1/5 in the denominator, I don't know what the cube root of 1/5 is, and I don't care. All I know is that it's going to be positive. So 3 times the cube root of 1/5, whatever it is a positive number. Here, when I plug in 1/5, the 5 cancels, you get 4 minus 1, I get positive over positive, the function is positive. The derivative is positive, so the function is increasing. And then finally here to the right of 4/5, I just plugged in 1. You plug in 1, you get the function's negative. And so now we can clearly see the increasing, decreasing behavior. At 0, it decreases and then increases, so I have a local min at 0. And then at 4/5, it increases and then decreases, so I have a local max at 4/5. And here in this question, we're specifically asked to also find the y-coordinate of these extrema. So in this case, I plug it in, and for 4/5, the number's not so nice, and that's okay. I just leave it in that form. You know, trying to square this or trying to do a cube, it's just not going to help, and it's kind of, to some extent, a little bit besides the point, since this is a calculus class. So here, messy number, that's fine. I just leave it in that form. You know, we found the local extrema. And as I mentioned, local extrema is a fundamental concept in calculus and is very important, if you know what I mean. So for the graphing problem, as I mentioned, the test is similar to the spring 2019 graph test. And so this slide, it's definitely good review for the theory, but certainly having to do this much work on the test would take too much time. And, you know, again, all this theory is really good. Understanding these number lines is really important. So for you, you know, for the test, we'll give you some information about the function, its derivative, its second derivative. And the question is, can you put all those things together? Okay. In this case, we would need to know the function to get the horizontal asymptote. But, you know, on the test, you'll be given all the information you need to figure out what the correct answer is. So here, typically, we start by putting in any asymptotes, and, you know, here we have an x-intercept at 0, and we have this inflection point at -1. So put those in. And so now, to me, you know, when we talk about graphing, what's the point of this material? To me, it's to understand how the derivative and the second derivative affect the shape of the graph and how they work together. So for example, in this section, up to the inflection point -1, you know, it's important that we understand, oh, it's above the x-axis, it's decreasing and concave down, and to me, it's all about combining the first derivative and second derivative behavior to get the actual shape. So I know if it's decreasing and concave down, it's going to have this, you know, shape right here. And so now I just fit it in. I just fit in that shape. And then I move on to the next section, you know, and it's about just synthesizing this information, putting all these different facts together. So here you can see it's positive, it's above the x-axis, it's decreasing concave up, decreasing concave up. So, and it has to go through the origin, and 0, 0, we have an x-intercept. So there's that piece. And now let me check this section up to the, up to the asymptote here. So here now it's negative, now it's below the x-axis, decreasing concave down, decreasing concave down. So it looks like this again. So here I have this shape here. And my final piece, we're looking at this section to the right of the asymptote. Again, you know, we're synthesizing. It's above the x-axis, decreasing concave up, decreasing concave up. The only way I can fit it so that it's approaching the asymptotes is like this. And so here we've synthesized the information, you know, given information about the function, first derivative, second derivative, can you put that all together and identify the curve? So here That's, that's what the sketch generally looks like. And I plotted the computer sketch next to it. And, for just having done this purely by hand, and I didn't even plot any points, this is a good sketch. It gets all the features. In fact, I kind of like this a little better because I can tell this is concave up, as opposed to here, it's hard to tell that that's concave up, So to me, even this hand sketch is kind of an analysis of the original graph. And this is a great sketch here. It's synthesized all the information. As I mentioned, though, it'll be more similar. The graphing problem will be more similar to what we saw in spring 2019, where you have a choice to choose from. And so for you, it's about analyzing the shapes and the behaviors. This problem, you can see, is a word problem. So the first thing is to realize that sometimes the brain gets a little, agitated with word problems. That's okay. And so now the thing is to carefully read the problem at least 2 times, I would say. So when I read the word problem, I'm looking for keywords. So here it says a cylindrical water storage tank is to contain 2,000 meters cubed. Find the radius and height of the container that minimizes the amount of material used, and then provide mathematical justification. So for me, the first word that sticks out is the word minimizes. Any problem that in Calc 1, or in general, but in Calc 1 for sure, that says what's the smallest, the largest, the most, the least, what minimizes, what maximizes, that's an optimization problem. And that's a key phrase I'm looking for that tells me this is an optimization problem. And now I know how a Calc 1 optimization problem goes. There are certain components to a Calc 1 optimization problem. So someone's asking if volume formulas will be provided. So first of all, they're asking about a crib sheet. There's no crib sheets. There's no notes. This is a closed electronic, no electronic devices allowed other than webcam. So I'll talk about the volume formula here in a second. So here, when we're trying to do an optimization problem, we're now looking for 3 things. Am I minimizing or maximizing? So here we're minimizing. The second thing is, what are we, minimizing or maximizing? Here we're trying to minimize the amount of material used, so you'll have to convert that to math. And third, what's the constraint? In a Calc 1 optimization problem, there's usually always a restriction that has to be satisfied. And so here, when we read, no matter what cylindrical storage tank we build, it has to contain 2,000 meters cubed. So that's our constraint. And the thing we're trying to minimize is the amount of material used. So here, we build this cylindrical tank, we start out with sheets of metal. So we need to know how much surface area this cylindrical tank is okay? And it's completely closed. It doesn't say the top is open. There's no reason for us to believe that it's not a completely contained water storage tank, okay? So now here's, here we've got the diagram, and we should set up the formulas. And so there's a question about the volume. And I noticed this on exam 2, that a lot of folks were not able to calculate the volume of this cylinder. And so, it's really important that you understand that here, all we have to do is calculate the area of the base and multiply by the height. That knowledge is, it's assumed that that you can do that, that's known. Anytime the cross section is fixed in one direction, you can just find the area of the base and multiply by the height. So here, the area of the base, which is a circle, would be pi r squared times the height, which is h. And so here, our volume formula is pi r squared h equals 2,000. And, one has to be able to derive this volume formula. It's a standard construction for finding volumes, If the shape in one direction is the same, if the cross section is always the same, then you can just find the area of the base and multiply by the height. So The other thing we need to calculate is the surface area. How much material do we need? And so for the surface area, it's important, the way I like to analyze this is I like to think, okay, let me cut this cylinder down the side here. Let me cut it and flatten it. So if I cut it and flatten it, it has this rectangular shape. And if you keep track of things here, this length around the top, that corresponds exactly to this length here. And this height, obviously, that stays the same. That's the same. That's this height right here. And, the circumference of a circle, we all know is 2 pi r. So here, this is 2 pi r. And the height is h. So we can calculate the area here is just 2 pi r times h. And so that's the formula I have. So here, 2 pi r h, that's the side, and then pi r squared is the bottom, and and there's two of them, the bottom and the top. So pi r squared is the area of the bottom, and times 2, so you get the bottom and the top, plus 2 pi r h, that's the area of the side. So adding all of those gives us the formula that calculates the amount of surface area required to build this cylindrical water storage tank. So this becomes our optimization problem. Minimize the function 2 pi r squared plus 2 pi r h, where pi r squared h has to always equal 2000. One thing I want you to notice is the function we're trying to minimize is in 2 variables, is a multivariate function. In Calc 1, the way we address that is we use the constraint equation to solve for one variable in terms of the other. Here I solve for h. I don't want to solve for r squared personally because it'll involve a square root, and then taking a derivative of square root is kind of a pain. So here I just solve for h. I get 2000 over pi r squared, and then I substitute that in for h right here. And so then, you get a function that's completely a function of r. And here I just do a little algebraic simplification here, where you can cancel the pi and one of the r's, and here 2 times 2000 is 4000. So I get my function here that I'm now trying to optimize. And it's now a function of one variable. And that's the whole point. To get a function to optimize that's in one variable, and now in Calc 1, we know how to do that. It's kind of the usual story where we're going to find and classify the critical points. So essentially this is now at this stage, once you've set it up, this is now just an Extrema problem. So for the derivative, I wrote 4000 over r as 4000 times r to the minus 1, because I'm going to use the power rule, the derivative of, a variable raised to n, you bring the n down, and then it's that variable raised to n minus 1. So here the derivative would be minus r raised to the minus 2. So negative 1 over r squared. So there's the negative sign from the derivative, and here's your r squared in the denominator, right? R to the negative 2. And again, I know I'm going to be looking for where the derivative is 0 or undefined. So let me combine these into a single fraction. So here what I'm going to do is I'm going to multiply top and bottom by r squared, the first term, so that everything is over r squared. And 4 pi r times r squared gives me 4 pi r cubed. And then you combine it, you get 4 pi r cubed minus 4000 over r squared. So the derivative is undefined at r equal to 0, but I claim here that r has to be greater than 0. Since r is measuring a radius, if we had, if the radius was 0, obviously the volume would not be 2000. So r has to be greater than 0. Therefore, the derivative is not, I don't have to worry about 0 being a critical point. So I'm only concerned with where the derivative is equal to 0, I'm not worrying about where the derivative is undefined, because it would be undefined at 0, but we're not allowing r to equal 0. So remember, a fraction is 0 when its numerator is 0. So move set that numerator equal to 0, move the 4,000 over, divide by 4, you get pi r cubed equals 1,000, divide by pi, you get r cubed equals 1,000 over pi, and then take a cube root. So we have r is the cube root of 1,000 over pi. And a cube root of 1,000 is 10. So, I said this before, when we find critical points, so we found a critical point here, we must now classify them. You have the option of doing a first derivative test or a second derivative test. Here, actually, second derivative test would not have been that hard and perhaps would have been preferable. Why do I say preferable? Because it's not necessarily easy to pick nice numbers to plug in, because I don't necessarily know what 10 over cube root of pi is. But what I did was I just kind of thought about it in terms of limits. So first of all, I'm not worried about the denominator because it's squared. So it's always going to be, greater than 0. Here, to the left of 10 over the cube root of pi, I thought about what happens as r approaches 0. Not equal to 0, but approaching 0. If you look at the numerator, as r approaches 0, this 4 pi r cubed term gets really small. It goes down really small. Smaller than 4,000, this is going to be negative. To the left of 10 over the cube root of pi, the function's going to be negative. And in the other direction, I'm not worried about the denominator. I'm asking, okay, what's going to happen when r gets really large? And again, we can see when r gets really large, 4 pi r cubed will get really, really large. And eventually this is probably bigger than 4,000. This is positive. I think in this case, it's probably better to maybe look at the second derivative, because you get 4 pi plus, because here, remember, r squared, that's really r to the negative 2. When you take the derivative, you're going to bring down a minus 2. So it'll be 4 pi plus 8,000 over r cubed. Yeah, that's supposed to be an 8,000 over r cubed. And 4 pi plus 8,000 over r cubed is always positive because r is greater than 0. If it's positive, that means it's concave up. If it's concave up, we have a local min. So this problem, I think probably it's better to take a second derivative to try and classify it rather than use a first derivative, because the numbers aren't that nice. But with this, when you take the second derivative, you see it's always positive. So there's, that's nice. So either way, using first derivative test or second derivative test, we can classify that there's this low point. I do want to mention one little subtle detail is that both of these tests verify that we have a local extrema. And in this case, however, given the geometry, since this is the only critical point, and based on the graph, you kind of see this is the only low point, this local extrema is also an absolute, this local min is also an absolute min. And for optimization problems, we're really looking for the absolute extrema. But of course, sometimes absolute extrema can occur where local extrema are occurring. That's what happens here. So I have an absolute min at 10 over the cube root of pi. I just want to make sure I answer the question. Sometimes the question asks for, sometimes they want to know what the actual area is or whatever, or sometimes they want to know the dimensions. So here they specifically ask for the dimensions of the cylindrical tank. So I've solved for R, and I use the volume, the equation for the volume, the fixed volume is 2,000. I use that to solve for H. And so here I solve for R and H, and having done the first derivative test, I know that this is a minimum. So yeah, to me, optimization is very important. And like I said, key things we're looking for is in the phrasing of the question, does it say smallest, largest, most, least, maximize, minimize? That's classic code for optimization problem. Then figure out what's the function you're trying to optimize. Usually it'll be a function involving more than one variable. And then what's the equation that has to always be true? What's the fixed constraint, you know? And then it kind of, at that point, becomes, you know, kind of mechanical. You convert it to a one variable problem. And so there's no graphing calculators allowed. So students asking about, if I have a graphing calculator, can I just plug in the equation? Yeah, if you could check the graph on your graphing calculator, but there's no, I mean, you know, it's test 3. I hope we know by now, there's no calculators or notes allowed in Calc 1, Calc 2, Calc 3, differential equations, matrix methods. Okay, so yeah, don't use a calculator. So Newton's method.
Ask a really quick question about the one you just went over.
Yeah, like this previous one.
Yeah. So on the test, how do you want us to write the answer? Is there any specific way, or can we just say, or just like write out R equals blah blah blah, and then like,
yeah, you can just say R equal, just, you know, like set up the optimization problem, do the derivative, find the critical point, classify it, and then answer the question. So if they say, what are the dimensions, just say R is this and H is this. Or if
Okay.
they want something else, you know, yeah.
Gotcha. Thank you.
No worries. So you can use any kind of function calculators. I can't believe I'm getting these questions on test 3. No calculators. And I hope you haven't been using calculators up to this point. And I'm going to assume you're messing with me. No calculators in A1350, 1360, 2350, 2360. Besides, you don't need a calculator. You know, that's the thing. Like, none of this stuff, I don't know that a calculator necessarily make your life that much easier. Especially not on the test I'm giving tonight. You know, it's been a tough semester just with the COVID, not to mention this horrible stuff we've had to deal with, this tragic stuff. So I'm just trying to write a straightforward test here, folks. Don't make it more complicated than it is. And, you know, just watch out for those little algebraic errors. That's where most of the mistakes tend to be, you know. All right, so Newton's method is very important because it starts this whole field of math called numerical analysis, okay? So here, this is a slightly tricky problem because it says use Newton's method to approximate the value of, and it says the critical point of the given function. So here, you know, Newton's method is a root finding problem. It solves the equation f of x equal to 0. Here, we're not trying to solve f of x equal to 0. Instead, we're trying to solve where the derivative is equal to 0. Or technically speaking, or where the derivative is undefined. But in this case, when we look at the derivative, we see that the function is a polynomial. So we know that it's defined everywhere. So in this case, the only place it could have critical points is where the derivative is 0. So this is my starting point for the Newton's method here. Not f of x equal to 0, which is the traditional problem. Here, I'm trying to start with f prime of x equal to 0. That's what I want to solve. So let me say this. It'll sound a little confusing, but then I'll show you. In Newton's method, in the formula for Newton's method, the f that we usually use is now f prime. Because we're not trying to solve f equals 0, we're trying to solve f prime equals 0. And so here, just to kind of make the notation a little clear, I don't know if this helps, I'm calling the derivative f prime of x. I'm relabeling the derivative as f prime of x. And now this is the problem we're trying to solve. Oh, and I see a typo here. I need to put a space here between the 0 and the we. So now this is the problem we want to solve with Newton's method. Not f of x equals 0, but g of x equals 0, where g of x is the derivative of f. So if you just use Newton's method, formula would look like this if you're trying to solve g equal to 0, and here g equals f prime. So for this particular problem, where we're trying to approximate the critical point, that's what the formula would look like. There's not an f up here, and this is not f prime. Everything has been increased by one derivative because our original equation has been increased by one derivative. We're solving f prime equal to 0, not f equal to 0. So now it's just kind of plug and chug. We know the derivative is x sub n to the fifth minus 11. The derivative of x to the fifth minus 11 is 5x to the fourth, and then I plug in an x sub n for x. And very last step here, you don't have to do this, but if it says simplify your formula, your answer or something like that, then this would be the next step, is I want to combine this into a single fraction. So multiply top and bottom by 5xn to the fourth. If I multiply top and bottom by 5xn to the fourth, then here, this numerator term becomes 5xn to the fifth. The whole thing will be divided by 5xn to the fourth. And we're subtracting, and it's important to put parentheses around here before you do the subtraction. So 5xn to the fifth minus xn to the fifth is 4xn to the fifth. And then this minus sign distributes to the minus 11, and that becomes a plus 11. So that's how I get this final simplification here. And this would be where we would stop. On a test, it's not realistic for us to ask you to calculate iterations. Really, this is meant to be done with a machine, so here, which aren't allowed on the test. So here, this is all we're looking for, And here, if it said, I don't necessarily have to put it together, but if the instructions say simplify your answer, then put it together. One other thing here is, essentially in this problem, what we're doing is we're approximating the fifth root of 11, because that's the root of this equation. If you just solve it analytically, the answer is fifth root of 11, but what number is fifth root of 11? Like, is that like 2 points, like 1 point, something? Like, what is it, So Newton's method now, this formula now, will actually start to calculate an actual usable number for the fifth root of 11, 1 point, whatever it is. So yeah, Newton's method is important. It's really important that you know the formula in general. We're not going to give you the Newton's method formula. So you should either memorize it or know how to derive it. It's not complicated to derive. And keep in mind, Newton's method is a root finding problem. We first set up whatever we're trying to solve, whatever problem we're trying to solve, we set it up as, in this case, g of x equal to 0. And then once you get it in that form, then we can set up the formula for Newton's method. And then the rest of it is sort of a plug and chug doing the math. So, I think one thing that's a little potentially confusing about this test is this is the first test that we have derivatives and antiderivatives. Okay, so it's just important to keep that in mind. And why I say that is because sometimes students will get confused, and I see this happen all the time, what I'm about to write here. I see this happen all the time, and I just want to warn you about it. So obviously what I've written here is wrong, but it's a very natural thing for students to do. So what I've written here is not the antiderivative. What I've written is the derivative, right? And so be careful when you're doing an antiderivative or a derivative, make sure you're going in the right direction. I've seen, when a student meant to take a derivative, but they took an antiderivative, or they meant to do an antiderivative, but they took a derivative. It's kind of natural in this setting, when we've kind of now introduced this new thing. So here we want to find the antiderivatives of these two given integrals. For the first one, neither one of them is difficult, but they both have this sort of little subtlety to it, and that's why I put it on the review sheet. For this first one, the number one thing I want you to avoid trying to do is to quote unquote distribute the integral. The integral of f over g does not equal the integral of f divided by the integral of g. So that's the first thing I want you to don't, fall for that kind of temptation. Oh, let me just put integral on top, integral on bottom. That just is not a mathematical fact. Here, what we should start to kind of get in the habit is just to realize that anytime in the denominator you have a single term, a single expression, or really anytime you have a denominator, but especially if you have this single term in the denominator, something we can try and do is break up the fraction into two fractions. And that's the whole trick to this problem. So once we break it up and then do the basic algebraic simplification, so you remember here we subtract the exponents. So here this would be equal to x to the 9/2 minus 4. 4 is 8/2. 9/2 minus 8/2 gives me x to the 1/2. And for the sine term, obviously the x to the 4th cancels top and bottom. We're just left with sine. And so after this algebraic simplification, what's left is, very straightforward to find the antiderivative of. For x to the 1/2, remember I'm finding antiderivative, not a derivative. We do, the antiderivative of x to the n is x to the n plus 1 over n plus 1. So here 1/2 plus 1 is 1/2 plus 2 over 2. That's x to the 3/2. So that's where the 3/2 is coming from. And then we divide by 3/2. So dividing by a fraction is the same as multiplying by the reciprocal of the fraction. So dividing by 3/2 is the same as multiplying by 2/3. And finally, for sine, you have to have your derivatives memorized, or however you want to think about it, antiderivatives. Here, I know the derivative of cosine by itself is negative sine. So if I just took the derivative of just cosine, that's negative sine, but here I have a plus sign. So here, if you put a minus sign in front, the derivative of minus cosine will give you exactly plus sine. And so there's our derivative. And you see I'm checking my answer by taking, there's our antiderivative, and you can check your answer by taking a derivative. So I differentiate 2/3 x to the 3/2, I better get x to the 1/2, and we do. Take the derivative of negative cosine x, I better get sine of x, and we do. And of course, sine of c is just 0. For the second problem, it looks very difficult, but if we manipulate it with some trig identities, then it becomes really straightforward. So the trig identity for tangent squared, so, if you don't know the identity, that's fine, but you should always know sine squared plus cosine squared equals 1. If you know that, then you can find all the other identities. So here, if I divide both sides, so remember, tangent is sine over cosine. So here, if I divide by cosine squared, both sides, then the sine squared, this term here, the sine squared over cosine squared, this term here, that becomes a tangent squared. And the cosine squared over cosine squared, that becomes a 1. And finally, on the left-hand side, the 1 over cosine squared, that becomes a secant squared. So here you divide both sides by cosine squared. I get sine squared over cosine squared plus cosine squared over cosine squared equals 1 over cosine squared. I get tan squared plus 1 equals secant squared. And now move the plus 1 to the other side to isolate the tangent squared. So I get tangent squared equals secant squared minus 1, which is surprisingly easy to find the antiderivative of, if we know our derivatives. So here, the derivative of tangent is secant squared. So I know the antiderivative of secant squared would be tangent. And of course, the derivative of theta is 1 here. So the antiderivative here, I copy the minus sign. And the derivative of 1 is just theta. So there's our antiderivative. It's not too bad if you know kind of how to approach it. Just looking at tan squared by itself, if I don't try something, it's a mess. I have to try something. Even if I write a sine squared over cosine squared, there's still, okay, I still need to do something. Then I might think to replace either the sine squared or cosine squared by 1 minus the other. Then that starts to give us a little traction. And it's similar to what we've done here. Remember, you can always check your answers by taking a derivative. But also, of course, it's really important that you know your derivative formulas. That's key. A sigma notation problem. So in all honesty, this type of problem is a little too involved to get into, but the main thing about this type of problem is the notation. And here, it's really important to start with the core and work your way out. And here, what I notice is there's a couple of things that can be done. This square can be distributed in this parentheses. And then this sigma can be distributed across the difference. And this 2 over n, it doesn't contain the letter I, and the sigma notation only cares about the letter I, so that 2 over n, I can actually pull it out of the sigma notation. I don't want to pull it out of the limit because it still has the n. The 2 you can actually pull all the way out. It doesn't have an I or an n. You can pull the 2 all the way out. But so here's, I just put it in front. So here's that 2 over n that I moved. I just moved it in front here. And here's the sigma that I distributed to each term. I took this sigma, put it on each term. And now here, the square, you put it on the 2. 2 squared is a 4, which is right here. Put it on the n. You get n squared, which is right here. So the 4 and n squared don't contain the letter I, so I pulled it out of the sigma notation. And then finally, the square goes on this I minus 1. And you see you have this I minus 1 squared right here. So the math is not difficult. The notation is really annoying. And it's really important you take some time to really look and see, exactly what you're looking at, to see exactly all the little pieces. Don't let the notation overwhelm you. So here, I now take this 2 over n and distribute to each term. Actually, before I did that, I noticed here, this sum we can add already. The sigma of 1, I going from 1 to n, that's just 1 added to itself n times. So this just equals n. And now I'm going to distribute the 2 over n. 2 over n times n is just 2. And the 2 over n, so there's your just 2. And 2 over n times 4 over n squared, 2 times 4 is 8. N times n squared is n cubed. So just being able to simplify it up to this point, that's really part of what we're just trying to learn how to do. And a lot of it is just carefully working through the notation, and certainly practice makes perfect. So at this stage, all that's left for me to do is to find this sum. And so get rid of all the i's and replace this with an expression involving only the letter n, and then take a limit using dominance of powers. And so here, again, if you look at the summand, what's the summand? This part here, the thing we're adding up, the thing we're summing, that we can still FOIL out. That's not been simplified. So I FOIL out the summand, and a minus 1 squared is I minus 1 squared is I squared minus 2i plus 1. And now I'm going to distribute the sigma. It's a very kind of mechanical procedure, and it goes step by step. And the actual math isn't difficult, but dealing with the notation can be quite irritating for sure. And practice makes perfect. So here I distribute the sigma to each term, and for that second term, I pull out a minus 2 because it does not have the letter I in it, and the sigma notation doesn't care about it if it's not the letter I in this case, because our index is I. And now using the given formulas, we can sum these up. And so this is the sum of this sigma notation here. These two things are the same. I can replace one with the other. And that's what we do. So you go back to the original limit here. Our limit looked like this that we were taking. And so now I replace right here. So this sum has been replaced with this stuff. And since I'm using dominance of powers, I actually calculated the highest term here. In the numerator, n times 2n gives me this 2n cubed. In the denominator, I'm going to distribute that n cubed on the next step, I guess. So here with this other term here, I cancel the 2's. So I just have n times n plus 1. And here now, if you distribute this negative n, look, negative n times plus 1 is a minus n, and there's a plus n, so these terms cancel completely. We just have a negative n squared. Now I distribute the negative 8 over n cubed. Remember, the 2 is just a 2. It never changes. So here, 8 times 2n cubed, 8 times 2n cubed gives me my 16n cubed. And in the denominator, 6 times n cubed gives me my 6n cubed down there. Here, negative 8n cubed, just multiply to negative n squared, because these terms cancel out. Minus becomes plus. I get 8n squared over n cubed, and I cancel. Then I send n to infinity and use dominance of powers. This term goes to 0 because there's an n in the denominator. This term, the leading term, is n cubed on top and bottom. So by dominance of powers, it goes to 16 over 6. Yeah, kind of a mess. But it's really about understanding the notation. At the end of the day, it's really about, can you understand the notation? You know? Here, this is a good problem. I'll do this really quickly and stop. This is a good problem. This is a relevant problem. The thing I want to mention to you is this is an approximation problem. So what does that mean? We want to approximate the integral. Specifically, the implication here is that n has to be a constant. If we're trying to find the exact area, n will be the letter n, okay? And so here, both problems, whether you're approximating or finding the exact area, we start by finding delta x. And once I have delta x and I know that the delta x is 1/2, I can find the partition. So honestly, for this type of problem where we're approximating, I personally don't even solve for the x sub I stuff, because you don't need it. And I don't even worry about, I just go right to the partition. See, once I know delta x is 1/2, starting from 0, just add 1/2. So starting from 0, I add 1/2, I get to the next point. Add 1/2, I get to 1. That's the next partition. Add 1/2, you get to 3/2. Add 3/2, you get to 2. Once I know my partition, I can just look now and pick out the left endpoints. Here's the left endpoint of the first subinterval, left endpoint of the second subinterval, left endpoint of the third subinterval, left endpoint of the fourth subinterval. And now I'm just doing height times width. And so here's my height at 0, height at 1/2, height at 1, height at 3/2 times the width. And then I'm finding the answer. You know, for the approximation problem, I don't worry about the notation too much. I don't worry about all that notation, the x sub I. You can, and you can certainly use it, it'll work, but you don't have to. For the approximation problem, once you find delta x, you can find the partition. Once you have the partition, then you can pick out whichever point you want, left endpoint, right endpoint, or calculate the midpoint. For the exact area problem, the formulas do help. All right, folks, I'm going to stop right here.